Okay, so welcome back to the fourth lecture on vector space. In today's lecture, we are going to talk about deletion theorem, basis and dimension, and some small problem related to basis. Okay, so first let's talk about deletion theorem. This is the statement of deletion theorem. Let me quickly walk you through the definition. It's saying that if a non-null vector space V, so vector space initially has to be non-null, it cannot be an empty one, over some field F, and it is spanned by a linearly dependent, okay, so this is important, a linearly dependent set, this is the set given, then the vector space can also be spanned by a suitable proper subset of S, okay, proper subset. Alright, so these are the two important things. So it's saying that if the vector space is spanned means all the elements of the vector space can be generated using the set S, where S is dependent, then it can also be spanned by a suitable proper subset of S. That means if I delete some elements from the S set, okay, proper subset means a set which is just smaller than the set S, and it is created by deleting some elements of S. Okay, so that means the vector space is generated by L of S. Now if I delete some elements from S, okay, suppose upon deletion I am saying that T is a subset of S, okay, so T has been is a proper subset of S. So now the linear span of T, this will also generate the vector space V. Okay, so S generates V, then T will also generate V, provided if S is dependent and we are deleting some particular elements from the S set, not any random element, some particular elements. That's why the word has been used, suitable proper subset. Okay, not just any proper subset, some suitable proper subset. So this process of deleting some element from the S set is called deletion theorem. Okay, so let's get into the proof of this. The set S is given to me. Okay, so here S given by alpha 1, alpha 2 and so on, alpha n is linearly dependent. Okay, now one small property of linear dependence I'll be using. So let me first quickly show you that property, then again I'll come back here and continue. Okay, so imagine some set, the given set only, alpha 1, alpha 2 dot 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 alpha n, this is linearly dependent. Okay, now as per the definition of linear dependence which we have done before in the previous lecture, there exists if I take this relation that if C1 alpha 1 plus C2 alpha 2 plus dot 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 Cn alpha n equals theta. Okay, so if I take this relation, then if this set is linearly dependent, there exists at least one non-zero constant such that at least one non-zero constant which will be satisfying this relation, right? So if it is linearly dependent, I can say that therefore there exists at least one Ci not equals to 0 such that if I call this one satisfies. Okay, so equation 1 is going to be satisfied provided at least one constant is non-zero. Okay, so now let's say that, let me assume, let Cj not equals 0 for some j equals 1 to n. So this would imply that Cj inverse exists in the field because Cj is non-zero, such that Cj inverse times Cj, that would be the multiplicative identity 1, correct? So now imagine I am keeping the Cj element, Cj alpha j element. Okay, now where will I find the Cj alpha j? Somewhere over here in the middle, somewhere in the middle I'll find Cj alpha j. Okay, so I'm keeping the Cj alpha j, let's say this is the Cj alpha j over here. I'm keeping that on the left hand side and taking everything else on the RHS. Okay, so taking everything else on the right hand side. So then I would have minus C1 alpha 1 minus C2 alpha 2, like this. I would reach minus Cj minus 1 alpha j minus 1. The Cj alpha j element is already here, so the next one would be minus Cj plus 1 alpha j plus 1 and minus so on until we reach Cn alpha n, right? This I would have this relation, keeping the Cj alpha j on left hand side, everything else being taken on the right hand side. Okay, now I am multiplying this relation by Cj inverse on both sides. So if I multiply by Cj inverse, you can see this Cj multiplied with the Cj inverse, it would give me 1, correct? So in the left hand side only alpha j will be remaining. Right hand side I will have these kind of things, Cj inverse C1 alpha 1 minus Cj inverse C2 alpha 2 minus Cj inverse Cj minus 1 alpha j minus 1 minus Cj inverse Cj plus 1 alpha j plus 1 minus Cj inverse Cn alpha n, right? Now all these are just some constants of the field. So these constants I can rename them as, let's say, P1, P2 and so on. So I'm renaming all these constants and I am saying that alpha j equals P1 alpha 1 plus P2 alpha 2 plus dot dot dot, and over here I would be having Pj minus 1 alpha j minus 1. The jth element is already on the left hand side, so that would be missing over here. The next one would be Pj plus 1 alpha j plus 1 and so on until Pn alpha n, right? So this is the relation that I wanted to talk about, that you can observe if the S set is linearly dependent, okay, and that means some Cj would be non-zero, okay. So now I am connecting the statements that I have built. If a given set is linearly independent, then there exists some Cj is non-zero, then corresponding to that jth element, okay, the index is j, so corresponding to that I have alpha j element can be expressed as a linear combination of the remaining other vectors of that particular set, okay. So this is the property that I wanted to tell you. So I'll just recap once again. If a given set is linearly dependent, okay, I'll just mark the words that I'm telling. If the given set is linearly dependent, then there exists some Cj which is non-zero as per the linear dependence definition. Corresponding to this jth index, the alpha j element can be expressed as a linear combination of the remaining other elements of the S set, okay. So now keep this property in your mind. So this is going to happen whenever a set is linearly dependent, okay. This can be treated as an independent theorem, okay, which I have not done, but right now you are getting that. So I'll come back to deletion theorem here and see how I can use the thing that I showed you just now, that here S is linearly dependent, okay. So now the moment I have this, I'm just going to use my previous theorem that I have done and I can say that then there exists some alpha j for j equals to 1 for some j, for some j equals 1 to n, such that alpha j can be expressed as the linear combination of the remaining others, okay, the thing that I showed you just now. Okay, so alpha j can be expressed as linear combination of the remaining other elements of the S set. So using the previous theorem, I have got something like this, and let me call this equation number 1. Okay. Achha. Now what I will be doing, I will be creating this proper subset of S and call it T. And how will I create that? Let T equals, from the S set I will delete this alpha j element. Okay, remember which one to delete. As I told you, it has to be a suitable proper subset, not any random one. The way of choosing the proper subset is by deleting this jth element corresponding to which the constant was non-zero in the linearly dependent condition. Okay, so the linearly dependent condition, which constant was non-zero, that corresponding element you can delete from the S set, and that will help you create the proper subset of S. Okay, so T is alpha 1, alpha 2, dot dot alpha j minus 1. I am deleting alpha j, so the next element will be alpha j plus 1, dot dot alpha n. Okay, so I have created my capital T set. So here obviously we can see that T is a subset of S, since I have deleted one of the elements from the S set. Okay, now we want to show that this T set, which is a proper subset of S, this also generates the vector space V. Okay, so it is already given to us or already known to us that S is generating the vector space V. That is known to us. Now with the help of this, we want to show that the proper subset T, this is also generating the vector space V. Okay, this is something we are trying to show. Okay, so now you can see that using one of the properties of linear span we have done in our previous lectures before. If T subset of S, then I can say L of T subset of L of S, right? I have done this theorem and I already know that L of S is equals to V. So that means we are getting L of T subset of V. Okay, let's call this number 3. Similarly, I want to show the opposite thing, that V subset of L of T. Okay, now how that can be done? We can refer to equation number 1 over here. And so you can all check one thing, that alpha j for any randomly taken value of j, okay, j taken from 1 to n, whatever value, alpha j is nothing but an element of the S set, right? And if you observe the RHS, okay, since in the RHS I have deleted the jth element, whatever be the value of j, and I have constructed the T set in such a manner that that particular jth element is not present, then you can see the elements on the right hand side are nothing but the elements of the capital T set, right? So the LHS is the element of the S set, RHS are the elements of the T set. So that means I can tell this statement that any element of S which is on the left hand side is a linear combination of the elements of the T set, right? So this is the statement that I want to say, that from equation 1, any element of S can be expressed as a linear combination, can be expressed as a linear combination of the elements of capital T, right? So this is the statement that I was saying, any element of S can be expressed as a linear combination of the elements of T. Now this is again a theorem, okay, this again falls down to a theorem. Using a theorem, we can say that whenever we have something like this, if any element of a set can be expressed as a linear combination of another set, then we can say that L of S is subset of L of T. Okay, so this directly comes from one of the theorems of linear combination, and I already know that L of S is equals to V, right? So I'm getting that V is subset of L of T, and I call this equation number 4. So now you can just see equation number 3 and 4. Combining 3 and 4, I can say that V is equals to L of t. Okay, so therefore from 3 and 4 I get that L of t is equals to V, and this is my necessary proof, right? So what we have proved over here, let's quickly summarize. We have proved that if something like this is given to us, let me write it over here, that if S is dependent and that particular S is generating the vector space, okay, then if I take a subset of the S set, okay, if T is subset of the S set, then L of this T will also be generating the V set, provided this T is properly chosen. Okay, provided the T is properly chosen. And as I told you, how to properly choose it? In the linearly dependence statement, whichever constant is non-zero, corresponding to that particular constant, the jth element you need to delete from the S set. Okay, so that is how you delete and create the subset, and that particular subset is going to generate the vector space V. Okay. So using this concept, now coming to the most important part. See what we can do, given a linearly independent set, okay, suppose a linearly dependent set is given to me, and what I do is, suppose the S, I call this S1 set, okay, or I call this, let's say, the S set. I apply deletion theorem. Okay, now remember dt stands for deletion theorem. Okay, I apply deletion theorem and I get T. Achha, here also at the same time S is equals to L of S is equals to V, that is told to me, that is given. I get a subset using deletion theorem, I get a subset T1, let's say, which is a subset of S. Okay, and what's the property of that? The property is L of T1 is equals to the same vector space V. Now again, we don't know whether T1, this proper subset that we have created, is it dependent or independent? We don't know. So two things can happen, that either the T set is independent, okay, or the T set is dependent. Alright, so these two things can happen. If it is independent, then the process just stops over there. We cannot find a proper subset of T1 anymore, okay, because when it has become independent, it has become, we have made it as small as possible. Okay, if we try to make it even more smaller, now it will not be generating the vector space V anymore. Okay, so linearly independence is the place that the deletion stops. Okay, you cannot delete further. But if it is dependent, okay, if it is dependent, then again you can apply deletion theorem on the T1 set. Now you can apply deletion theorem and you can obtain, let's say, a T2 set which is subset of the previous T1 set, such that L of T2 will be still generating the vector space V, and again you don't know that whether T2 is dependent or independent. So again two cases may arise, that T2 is independent and T2 is dependent. So again, as I told you, if it is independent, the deletion stops, and now T2 is the smallest possible set which is generating V. You cannot make it more small. If it is dependent, you can again apply deletion theorem and obtain a T3 set which is subset of T2, such that T3 would be generating the vector space V, and again you can branch out T3 into parts, dependent, independent, and this process, this tree process will go on. Okay, now the question is, how long will it go on? If I tell you that V is finite dimensional, or if I tell you that V is finitely generated, okay. Now what is the meaning of finitely generated? Finitely generated means here every time some set is generating V. Initially S was generating V, then T1 was generating V, then T2 is generating V. So these are all generating sets. If I say that V is, the vector space is finitely generated, that means there exists a finite set which will generate the V set. That means linear span of that particular finite set will be equals to V. It's not infinite. So if it is finitely generated, and since we started with S, which was a finite set, okay, which was a finite set, so after n number of deletions, okay, let's say these are the number of iterations going on, so after maximum k steps, okay, where k must be less or equals n minus 1, okay, maximum you can delete n minus 1 number of times, because the set n has cardinality of n, so you cannot delete all the elements. Okay, if you delete all the elements, nothing will be remaining, it will become a phi set. Okay, so maximum you can delete n minus 1 times. Then in that case, in the worst possible case, if you delete or if you run this process n minus 1 number of times if required, then you will come down to a set, let's say Tn minus 1, which will consist of only one vector. Since you have deleted all the remaining vectors, n minus 1 times deletion has been done, so only one vector is remaining, and we know that a set which contains only one vector is definitely linearly independent, so the process has to stop somewhere. Okay, so the process has to stop ultimately when you have done a maximum n minus 1 number of deletions. Okay, and maybe it can happen that after 2 or 3 number of deletions you reach the independent place and the thing stops. In the worst possible case, you may have to delete n minus 1 times and obtain a set which contains only one element, and that one element is definitely linearly independent. Okay, now why did I continue deleting n minus 1 number of times? Why did I keep deleting and keep deleting? What was the purpose of deleting? What we are trying to do, we know that every time one thing is remaining constant. If you observe, whatever set we are getting, it is ultimately generating the vector space V. So this particular concept remains constant, that whatever set we are getting, it is generating the vector space. But we are very much interested in that particular set which is the smallest one such that it is generating V. Okay, so we want to create the smallest set. That's why we are going through a process of deletion. Okay, we are going through a process of deletion and we are trying to get the smallest possible set which will generate V. And how to understand it is smallest? The moment it becomes linearly independent, that means it has become the smallest set. Now, why are we again interested with the smallest set? That particular smallest set which has generated the vector space V and which obviously has become linearly independent, that is called the basis of a particular vector space. Okay, so here comes in the concept of basis. Alright, so I will come to the definition of basis now. What is basis? If V is a vector space V over a field F, a set of vectors in V is said to be a basis if, first of all, you can see the definition, S is linearly independent, okay, and that particular set is generating the vector space V. That means the thing which I was telling you right now, that it has to generate V and it's going to be linearly independent. That means we have, initially we had the dependent set, we started deleting, and after some time we reached a stage where the set became independent and it was still generating the vector space V, and at that particular stage, that set where we have stopped our deletion is going to be called the basis of the vector space. Okay, so here is the particular definition. The set has to be linearly independent and the set has to generate the vector space V. Okay, and what is dimension? It is just the cardinality of the basis set. Okay, that means the number of vectors in the basis. Okay, suppose you have a basis containing 5 elements, then 5 will be the dimension of that particular vector space, and dimension is represented by dim of the vector space V. Okay, so now we move on to a theorem which is saying that there exists a basis for every finitely generated vector space. Finitely generated means a finite set is able to generate the vector space. Okay, so that means the basis set is finite, it's not infinite, and such a basis will always exist. Okay, this we are trying to prove. Now, actually I will not write anything here. I have already done this proof right over here. It's already done over here. How is it done? First, I will take an S set which is generating V. Now, how can I take the S set? Obviously, I can take it because the V vector space is finitely generated. If something is finitely generated, then there exists some S which is subset of V such that L of S would be equals to V, right? So definitely we can get some set S which is generating the vector space V. Now just come back to this branching diagram that I have done. So now S can be either independent or dependent, right? This S set can be either dependent or independent. If it is independent, then see, it is satisfying the property of basis. For basis, what do we need? First, this is the first criteria of basis, that it has to generate the vector space, and the second criteria is it has to be independent. So the moment this happens, we have got a basis. If it doesn't happen, if this is dependent, okay, if this is dependent, then using deletion theorem, just the branching diagram which I did before, we will get some S1 set which is a subset of S such that L of, which is a subset of, S, such that L of S1 would be still generating V. So our first property is still maintained over here, and now S1 can be again independent or dependent. Okay, the branching thing that was happening, if it is dependent, then it becomes the property, required property 2, and S1 becomes the basis. If not, the process continues. Okay, and just like I told you, how long will the process continue? Maximum n number of times, n minus 1 number of steps, provided if S contains n elements. Okay, if S contains n elements, then this process of deletion can be done maximum n minus 1 number of times. Then we will be reaching a set having only one particular element, and that one particular element definitely becomes independent, and hence we get a basis every time. Okay. So coming to our last question of this lecture, we are going to show that this particular set is a basis of the vector space R3. Okay, so this set has 3 elements. Let's say this is my alpha 1 element, this is my alpha 2 element, and this is my alpha 3 element. So we have 3 elements, and we want to show it is a basis of the vector space R3. So the vector space here is R3. Now remember, whenever you are trying to show something is a basis, you need to show 2 things. Number 1, it is independent. So S is independent. That's something which you want to show at first. And number 2, you want to show that the S set is generating the vector space. In this case, the vector space is R3. So these are the 2 things that you would want to show to prove that S is a basis. Now to show S is independent, you can remember in my previous lecture of independence and dependence, I had told you that if the number of vectors 1, 2, 3 matches with the dimension of the vector space. Okay, so we have 3 vectors which is matching with the dimension of the vector space, then the easiest way or the fastest way of determining whether it is independent or not is by taking a determinant, right? So I'll just take the determinant of the elements. The alpha 1 I'm putting it, which is 0, 1, 1, alpha 2 is 1, 0, 1, and alpha 3 is 1, 1, 0. So if I calculate the determinant, let me just do that quickly over here. First of all, I'll have 0 minus 1, I'll be having bracket minus 1, and for the other one element I'll be having 1, so that would be 2, which is non-zero, right? So I have the determinant value 2 and it is non-zero. What we are interested in is the determinant 0 or non-zero? That is what we are interested, not with the exact value. If the determinant was 0, then what was our conclusion? If you can remember from the previous lecture, if the determinant value is 0, we can say that the S set that we have taken, S is linearly independent, right? And if the determinant had turned out to be exactly 0, then we would have said S is dependent, and hence this can never form a basis. Okay, so the first required property has been satisfied. We need to come to the second one. Okay, Achha. So we want to show this is a subset of that particular set. So what we are trying to do here is, if I call it A, we are trying to show LS subset of R3, and B, we are trying to show R3 subset of LS, right? So if we are able to show these two things, we can say that our required criteria is going to be matching. Okay, Achha. So now how to show these things? Let me take a random element from R3, let's call it eta, and I would like to show it belongs to LS. Then I'll be able to prove the part B of number 2. Okay, so let me take a random element that let eta belongs to R3. So that means eta would be some 3-dimensional coordinate. Okay, so let's call it A, B, C, where each of the elements A, B and C have been taken from real numbers, right? So I've taken a 3-dimensional coordinate where each input has been taken from a real number. I want to show it belongs to L of S. Okay, that means let me consider the relation that let eta is equals to, if it has to belong to L of S, then that means this element must be written as some linear combination of the elements of S. It must be possible to write it if it at all exists in L of S. Okay, so let me assume it exists, and let's see whether it turns out to be true or not. Okay, so let eta be some linear combination of the elements of S. That means C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3. Okay, now I'll just put the values. Eta has been taken as ABC. Alpha 1 that was provided in the question, alpha 1 was 0 1 1. Okay, so alpha 1 was 0 1 1. Alpha 2 was the next element, which was 1 0 1, and alpha 3 was 1 1 0, right? So that means if I compare all the x coordinates, right? If I compare all the x coordinates, I'll be having the equation C1 into 0 plus C2 into 1 plus C3 into 1 equals to small a, right? Then the second equation, if I take the y coordinates, I'll be having C1 plus C3 equals B, and C1 plus C2 equals C, right? So I have this kind of 3 equations. Achha. I am interested to knowing that whether these constants, the constants that I have taken, whether they actually exist or not. If they exist, then this relation is valid. Okay, if the C1, C2, C3 values exist, then this relation is valid. If C1, C2, C3 does not exist, then this relation is not valid. Okay, but we want to show that this relation is valid, only then we will be able to show that eta belongs to L of S, which is our target. So that means we are trying to show that some value of C1, C2, C3 exists. Remember, we are not interested with the exact value of C1, C2, C3. We are not interested with that. We only want to know whether some value of C1, C2, C3 exists or not. If it exists, then what is the value? We are not interested. Just whether it exists or does not exist. That's the question, that's the answer we want to know. Okay. Now, you can observe this is a system of linear non-homogeneous equations, right? Why non-homogeneous? Because you have constants on the RHS. Now, if you can remember, using Cramer's rule, okay, Cramer's rule, okay, if people have forgotten what was the condition for existence of solutions of non-homogeneous and homogeneous equations, then a link up here will be visible to you, one card will be visible to you, and that will that is one of my lectures of nature of solution of homogeneous and non-homogeneous equations. So you can go into that lecture and you can see it carefully, what are the conditions for the existence and non-existence of solutions. It is very well explained there, and then again come back here and understand this part. If you already know it, then no need to refer. Achha. So using Cramer's rule, if I take the coefficient determinant, okay, the coefficient determinant part, that means the determinant which I have just now taken before, which is 0, 1, 1, 1, 0, 1, 1, 1, 0, okay. And if I find the value of this, I have already found the value, it turned out to be 2. If the coefficient determinant is non-zero, then we would say, our conclusion would be, this system of equations, if I call it 1, then this system of equation has a unique solution if the coefficient determinant was non-zero. If the coefficient determinant was 0, then this system would have either infinite solution or no solution, and we would be able to decide which one depending on the rank of the coefficient matrix. Okay, that was a little bit complicated. Okay, so we won't go into that at all right now. So here the main thing is, if the coefficient determinant is non-zero, then this system of equation has a unique solution. Okay, so we can say that therefore 1 has a unique solution. Okay, and this comes from Cramer's rule. Now, as I told you, we are not interested with the exact solution of the C1, C2, C3 equation. We are not interested. We want to know whether the solution exists or not. And using Cramer's rule, we can see, yes, a solution is existing and it is also a unique solution. So the solution is existing. We have got that. So therefore, we can say that this equation that I have written, it is valid because the values of C1, C2, C3 are existing. So therefore, eta belongs to, if this relation is valid, that means eta belongs to, the right hand side was linear combination of which set? Linear combination of the set, we were calling it the S set, right? So it is a linear combination of the S set, that means eta belongs to L of S. So initially I had started from the point by taking eta belongs to R3, and I have reached the point that eta belongs to LS, right? So that means I can say that therefore eta belongs to R3 implies eta belongs to LS, and that would mean R3 subset of LS. Okay, and we can call this the small b, we can give it a name, because as I told you, this was the B part that I wanted to show. Now I will try to show the A part. Showing the A part is rather much easy. Okay, so I'll come to the A part. In the A part, I'm trying to show LS subset of R3. So as we already have seen that here, S is a subset of R3, right? Because S is a set of 3 vectors and those 3 vectors are taken from R3 itself. So it is definitely a subset of R3. And I have done this theorem in my previous lecture. I had told you that if I take L of any vector space, okay, if I take L of any vector space, then nothing new is going to happen. You are only going to get back the same vector space. Okay, I had explained you this concept before in my previous lectures. If I take linear span of a set which is itself a vector space, then you get that vector space back. You don't get anything new out of it. So here, if I using this kind of property, that S subset of T, if I have this, then LS would be subset of L of T. Okay, so using this property, if I take L on the left hand side, then on the right hand side, as per this property, I would be having L of R3. Since L of R3 is a vector space, so in place of, if I vector space, if I write R3, so my answer would be also R3, because R3 is a vector space. So L of R3 would be simply R3. Okay, and this is my small a part. So combining A and B together, I can say that therefore LS equals R3. Okay, and that is condition number 2 of the basis. Remember, we have already done condition number 1 over here. And this was condition number 1, that S is linearly independent. Okay, so that was condition 1, and condition 2 we have got that LS is equals to R3. So I can say that therefore from 1 and 2, S is a basis of R3. Okay, so this becomes a problem where we showed that some given set is a basis of some vector space. Okay, so see you in the next video. Thank you.